Thank you, everyone, and good morning. Welcome back from the break. First of all, let me just make a definition of AIOps for us so that we understand the context of what we're talking about here. So AIOps, which is artificial intelligence for operations, is the application of AI and machine learning and now generative AI to automate and improve network operations. And there's three use cases here that I've put on the chart that you may recognize. Proactive failure, anomaly detection, so predicting what's going to happen in the network. Generating actionable insights for optimization decisions based upon what you're seeing happening on the network. And then automation of workflows and even DevOps acceleration is another use case as well. Now, this is not new. In fact, this has been around for a while. We've been talking about AI, ML, and operations and how it can change the way we operate the network for at least 5 years. It's been topics of this conversation and this conference for at least that long. But why haven't we been able to implement it? What's been the challenges around getting that to a point where we can actually use it for the promise of what it can deliver? Well, I put it to you, I think there's two challenges that have affected our adoption of this technology. The first one is use case accuracy. So we've applied these techniques to data in the network, but we're generating outcomes from that predictive use case, which are only, at best, 80% accurate. That means 20% of the time they are wrong. And that's not good enough for an operator to take that advice and do proactive things on the network. 20% of the time, that action may be invalid or not required. So that's the first challenge. The second challenge is it's been very proprietary. The AI, ML capability, the development of that has been very problematic. It's very, very specialized. When I first took over an AI, ML group, there was about 8 developers in there. They're all data scientists. And I went to them and I said, okay, this is great. Really like the technology. When can I see a demo? When will you know if you got something interesting that we could show our customer? And the guy thought about it for a while, and he came back to me and he said, come back in 10 months and I'll let you know if it works. I said, 10 months? Can I not give you more developers? No, this is very specialized. We need data scientists. Come back in 10 months. So that's how the environment was then, and I think that's the reason that it never got adopted. So what's changing now? So now we are finding that in a multi-layer use case, where we've got a converged network of IP and optical and managed all from a single system, we can actually generate use cases by correlating data between those layers using the AI, ML derived techniques that we have to correlate information between layers. And that is proving very useful. And I'll show you some of those use cases as part of this presentation. The second thing, of course, is large language models. Just an illustration, but really it's the development toolkit that comes along with that, not just the large language model itself. We've talked about that with ChatGPT and all the other things, but if you go to any cloud provider now, they will fall over to give you a development environment which has a whole suite of AI tools, generative AI, cognitive search engines that are available and very usable for the general software developer. So now I actually have a team of 300 people who want to do AI development as opposed to 6. And I think that's going to make a huge difference as well. So we're ready. It's prime time. The other thing we've heard this week is that AI is all around us. Part of the reason is it's so accessible to everybody. It's going to happen. And it's happening now within our industry, and it's going to happen with operations. First of all, let me just give a bit of context of what I'm responsible for at Ciena. So I run the engineering organization that builds the Navigator Network Control Suite, otherwise known as MCP, if you remember that from as an operator. But that's a suite of applications that manage our entire Ciena portfolio. Consists of a multi-layer domain controller, which manages all layers of the network, from optical to OTN to Ethernet and IP. And we do that by modeling the whole network in a very normalized, structured model that discovers network information and constructs and then we manage on top of that with intent-based management. And that's deployed in the majority of Ciena customers around the globe today. In addition to that, we have a set of applications that sit on top of that controller that provide additional insights into the systems. Some of these use algorithms that you could claim to be rule-based AI already, but it's rule-based AI. Things like traffic management, IP applications, or liquid spectrum, which allows us to tweak the individual optical parameters of our coherent modems to maximize the performance of the optical network. And of course, then we have multi-layer applications which combine those things together and correlate the information between the underlay and the overlay. The third component of our organization portfolio is what we call the emulation cloud or digital twin, which is a very popular conversation that we've had this week. And that allows us to stand up not just the management system, which of course is all software, but we have a completely simulated network infrastructure as well. So we can stand up a whole network in this digital twin and of course play around with that, doing potentially scenario testings, large-scale testing, and also OSS integration. So this is available to our partners and our customers so they can use the APIs and access a fully emulated network at scale to test their overall systems, but also validate the operations of the software as well. So that's our complete software portfolio. In Ciena, we have a team of about 600 software developers working in the space. So it's a very significant investment for us and part of one of the reasons why we obviously, it's very critical to manage the complete network that we have from Ciena. So that's my development organization. And of course, they're very excited now because this is a very modern software architecture, but it's going to get revolutionized with AI ML techniques, and we'll show you that in the next set of use cases. So let's go through the 4 use cases that you're probably very familiar with, and you've heard maybe many speakers talk over the years about these, but I want to show you how they're changing a little bit and why I think they're ready for prime time. So first of all, proactive maintenance. So proactive maintenance we've heard about, and you could see, and you've probably seen examples of where we've tried to monitor the IP traffic and IP traffic patterns to determine what's going to happen in the IP network so that I can preventively take actions to stop congestion, to stop problems that may be occurring in the future on the network. That's a very difficult problem to solve, and as we know, not accurate enough. So you have to collect an enormous amount of data, and you can't get the accuracy you need to actually make an informed decision. But if you combine that with the multi-layer piece of that, if you actually apply supervised learning to the optical transport, the underlying optical transport, and then correlate that information up to the IP layer, now I can predict IP outages based upon what I'm seeing in the underlay transport. And I'll give you an example of that. We use machine learning, supervised learning for looking at the receive power levels of our optical lasers, and you can highly correlate the receive power levels and the changes in the receive power levels with eventual failures of that laser. But of course, once the laser fails, it's too late. But using machine learning now, we can predict when that's going to happen by watching the progressive changes in that receive power level. So now correlating that up, if I'm seeing that a particular optical link is potentially trending towards failure, I can correlate, well, what IP services are running over that link through the tools that we have, and I can take 2 actions. I can change the optical power using our liquid spectrum applications, which will allow you to adjust the capacity potentially in that optical link, give you a bit more capacity and a bit more life span on that optical link. Or I can take proactive action at the IP layer and switch the traffic away or steer the traffic away from a potentially troublesome link that then I can go and provide maintenance on later. So now we've got a use case that's useful and applicable. Second use case I want to talk about is service assurance. So the first one was trying to find a problem before it occurred. Now, what about when the problems occurred? How do I do rapid troubleshooting using machine learning to fix the right problem, not the wrong problem? And again, assuring an IP service can be quite tricky, quite difficult, especially when you're looking at all the different attributes that are part of that IP service configuration. But if you correlate that down to the underlying transport layer, again, applying machine learning techniques, this time it's reinforcement learning. We're applying reinforcement learning techniques to the behaviors of that optical link to then correlate that up into the effect on the IP services. The technique we use is called optical time domain reflectometer, which is OTDR. And this sends a pulse of light and measures the reflection in that fiber. If there's a fiber cut, the reflection is pretty obvious. But if you get a bent fiber or a dirty connector, or maybe some impairment on the equipment and the line itself, then that reflection can be quite subtle. What's interesting on the OTDR, it will also give you the exact measurement of how far down that fiber that reflection is happening. So I can pinpoint geographically where that connector is, where that fiber cut is, obviously, or where that impairment is happening. So that's a very handy and very useful tool for troubleshooting optical networks. But when we're looking at the measurements and the characteristics of what we measure on that OTDR now, we can use supervised learning to actually detect smaller increments, smaller impairments on that OTDR trace, and then correlate that to a dirty fiber, a loose connection, or something maybe more specific in your network. Could be temperature variations or even geographic locations, depending on where your fibers are. And you can see that in the map. We can, again, with OTDR, we can map this pinpoint exactly to the physical location of that impairment. And what we're showing here is several spots on the fiber where we've measured this OTDR, and it's come back with some impairment that's not quite clear, quite pure. And then on the left-hand side of the table here, we've actually tried to characterize those against what we suspect is the problem. So probable causes of fiber events through reinforcement learning of the characteristics of that OTDR trace. Now, if you map that against, again, the IP services, now you can understand, well, if I'm seeing maybe some IP service interruptions or link flapping behaviors in my IP network, I can go to the optical network and look, well, I don't have a fiber cut, but am I seeing the right level of optical transport capabilities that I expect, or I'm getting a combination and an additive effect of maybe optical impairments, which is affecting my IP service. So now we can use machine learning for intelligent troubleshooting of that transport space, giving you a more accurate way of assuring your IP service. Okay, so those are probably use cases you've probably seen before. Again, ones we've done but never been accurate enough. Now combining it with multi-layer, it makes it a much more useful technique and something that we're using in our systems today. Generative AI, that's the one that now becomes more mainstream, and some of the conversations that we're having now and quite exciting with everybody. And of course, this is all about using large language models, things like ChatGPT, but not just ChatGPT, but augmenting that with additional information using retrieval augmented generations for actual bringing systems in. So ingesting the documentation from our products, ingesting the REST API, and the system data itself. So what's happening on the system, now you can create a new user interface for the system itself. So today, an SDN controller has two ways of interacting with it. A UI, as you can see here, a graphical user interface, or an API. And in the future, there's going to be a third, which is a language model. And that's the way it's going to make a difference to operations. We're going to have several ways of interacting with these systems, and the language model will be one of them. And that will be the way that we can automate a lot of the functions that are very manual today in the UI. The other secret about this, what we're working on, is model chaining. So chaining the models from documentation to system to code together. And I'll give you an example here. We've got workflow acceleration. Here I'm just using a very simple example of a prototype we're working on we've ingested our documentation, so I'm going to ask the system here to give me the steps to provision a layer 3 VPN service. This is the user manual, so these are the instructions that you would follow on the UI itself. So if I was following the user interface, I would go through these steps, add these parameters, make sure I've got the right attributes in the right order, and enter that via the UI. But what this technology can do for us now is, rather than doing that on the UI, I can do that through a large language interface directly on the system. So now I'm asking the Navigator system, can you please connect to that SDN controller? I've got a template here, which was already previously done, a JSON file, and provision that IPVPN service with that JSON template that payload example that I had previously put together. So, and that's what the system will do. So it's just showing you that, of course, if you're doing that through this interface, it will show up in the UI, because the UI is real time. And as you can see, I actually provisioned a layer 3 VPN service on my SDN controller through a language interface as opposed to the UI interface. So now I've automated that operational task, which is point and click through a user interface with a language model. Last thing I just want to quickly, because we're running out of time, is, of course, the next item we can accelerate is SDN programming. So if I'm writing a client on my API, again, I can ingest the API information into this language model, and now ask it to write the code for that integration. So what are the corresponding REST API calls? And now I use the code generator to generate the code. Now that's not going to be 100% accurate, but it's probably 80% of the first start of what a designer needs to do in order to integrate into an API. So it can rapidly accelerate your SDN programming or OSS programming interface using code generation. Okay, so final remarks. We feel that use case for using and leveraging finally AI/ML is multi-layer. Multi-layer correlation allows you to get that capability. And large language models and tools are now available prime time to automate operational workflows and accelerate the writing of SDN applications. Thank you.